Welcome back to the Hackaday Remoticon. I'm contributing editor Tom Nardi, and I'll be introducing our next guest, who is perhaps best known to Hackaday readers as the creator of the Open Book, a very impressive and I think very important project that aims to design a fully open hardware ebook reader. But he's recently found himself with a new obsession, and today he's here to talk to us about the lowly segment LCD, specifically how they can be reverse engineered and ultimately bent to our will. So with that, please join me in welcoming Joey Castillo to Remoticon.
Awesome. Awesome. Thanks so much for that introduction. So I'm Joey, and my talk today is about kind of an old school display technology, segment liquid crystal displays. We have a lot to cover, but before I start, for those of you who don't know me, I figure I should do this. Who am I? And I can probably share my screen for this part. Let's click on screen share, desktop 2. Okay, great. Who am I? I'm at Jose Castillo on Twitter, where I share a lot of my process working on open source gadgets. A little while back, I designed this thing called the Open Book, which Tom just spoke about. And then recently, I've been working on the Sensor Watch. It's a board swap for the Casio F91W wristwatch, which is in pre-launch at Crowd Supply if you want to check out that link down there. It's in working on this latest gadget that I've learned a lot about LCD displays, these sort of old school, low cost, low power displays that you can find in lots of gadgets, from watches to pocket calculators. They're ubiquitous, they're cheap, and they're seemingly ideal for repurposing into hobbyist projects. Before we get to the talk though, let's just overview what segment LCDs are. They're generally small glass displays, and they tend to be monochrome, just black and white. They're very low power. This makes them attractive for battery-powered gadgets like wristwatches and digital thermometers, but could also make them attractive for DIY projects that want to use energy harvesting or solar power. And finally, they have a fixed layout, which is to say, you can't display arbitrary shapes on them. You're limited to turning individual segments on and off. This makes the layout of the LCD crucial to how useful it can be for your project. The display up top, for example, with just 3.5 digits, won't be as versatile as the display on the bottom with 8 alphanumeric characters. This is why I'm super into repurposing the LCDs from existing gadgets. These displays tend to have useful layouts for displaying a lot of information, like this Casio calculator watch. They're also often thoughtfully designed by, actual designers who do this for a living. This makes their designs nice in a way that industrial LCDs often aren't. They also tend to be thinner and finer pitched than off-the-shelf LCDs. The F91W LCD is sort of staggeringly thin. It's only 1 millimeter thick, and it's small enough to fit in a 38mm watch case. The finer pitch also allows for more segments to be addressed in this already small area. They're also just fun. Here's a watch with the Sensor Watch board swap installed. I've taken the F91W's display, which is only meant to display the time and date, and I've repurposed it to be a temperature display, 76.6 degrees Fahrenheit. Now, it's not perfect. The 7 is sort of a shorty lowercase 7, and the decimal point is a hyphen since there's no decimal point in this design. But if you're willing to embrace the limitations, you can take a small, well-designed display and coax it into doing all kinds of interesting stuff. Okay, so let's set the agenda. Today, I'm going to talk about how you can find these LCDs in the wild and bend them to your will. First, I'm going to introduce segment LCD tech, show off some of how it works, and explain what's required to drive very basic LCDs. Next, we're going to look at more complex LCDs through the lens of the classic wristwatch that I used to build the Sensor Watch. Then we're going to use what we learned in sections 1 and 2 to reverse engineer the LCD in a much more complex watch. And finally, if we have time, I'm going to share some of what I learned designing a custom LCD of my own. So that's a lot. So let's jump right into it. Chapter 1, Intro the Tech. I figured I'd start with a compare and contrast with a technology a lot of folks here are probably familiar with, segment LEDs. On their face, they look kind of similar. Each segment has a pin, and there's also a common pin. So for a 7-segment display like this, you'd need to run 8 wires to each digit. I've drawn a diagram here for how that works, and I actually found that I had to draw 2 diagrams, because you'll always find that these segment LED displays are either common cathode or common anode. That's because for a segment in the display to glow, current has to flow from the anode to the cathode. It's a complete DC circuit. You'll still use 8 wires with an LCD, but the first difference is in how the display works. Current doesn't really flow anywhere in an LCD. Instead, Segments are energized when a difference in voltage exists between the common and the segment electrodes. You can imagine an LCD segment as being a little capacitor, with the special property that when there's a difference in charge between the segment pin and the common pin, it will darken and become opaque. That common pin is neither anode nor cathode, because you drive an LCD with an alternating signal. Sometimes COM is high, other times it's low. LCDs don't like a static charge building up on either side, so you have to alternate the polarity of the charge. What do I mean by that? Well, here's what it looks like. And I beg you, please stick with me through these scope traces. I promise they're going to make sense by the end. The voltage differential between the common and segment pin has to be above a certain threshold for a segment to turn dark or energize. Typically, that's between 3 and 5 volts, but let's just go with 3 for now. Here, we're looking at one common pin in cyan and one segment pin in yellow. The difference between the two is in purple. You can see that when the common and segment pins get the same square wave, there's no voltage difference, and the segment is not energized. But when the segment pin's wave is inverted relative to the common pin, suddenly the voltage differential is plus or minus 3 volts. That's enough to energize the segment. The cruxy bit is that this has to be an AC signal with no DC bias. The frequency will depend on some factors, but don't worry about it too much for now. For now, let's give it a whirl, and let's do it really simply. This is a circuit Python script, and it should be easy to see what it's doing. It's setting up digital outputs for one common pin and a bunch of segment pins, as well as a button input. When we loop, we repeatedly set COM high and low by toggling this phase variable. If the button is up, we set all segments to the same value as COM, which gives them all the same square wave. But if the button is down, we set our on pins to the opposite value, giving them the opposite wave. So let's check it out. So here I have my Metro M4, which I've set up with this button, and my wire is going to the display. So the COM pin, I've actually tied to the LED here, so you can see it flashing high and low. That's actually the frequency of the wave we're feeding this LCD. So we're not talking megahertz or even kilohertz here. This is in the dozens of hertz. You can see it with your eye. So right now, they're all getting the same square wave. But when I press the button, it's energizing the segments that are saying high by inverting the wave on those segments. I also have my little pocket oscilloscope here, and it's showing the difference between COM and seg, which is 0 until I press the button, and then it becomes plus or minus 3 volts. Okay, so that is section 1. To recap quickly, LCD segments are basically little capacitors that turn dark when they're charged. These displays are low power because current isn't really flowing anywhere. They do need to be driven by an AC signal. This part is important. The astute viewer might be thinking, hey, I could energize a segment by holding COM low and seg high. And that is true, you could, but it'll break your LCD after a while, so don't do that. Finally, the key is to keep the driving voltage across the segment below the threshold to turn the segment off and above the threshold to turn the segment on. Keep that in mind as we move right along to section 2, multiplexed displays. So at this point, you should have the gist of how LCDs work. Now we're going to take these basics and apply them to a more complex display, the display on our dear friend, the Castillo F91W. So you'll notice there are a lot of segments on the left there. They're all driven by the row of pins on the top of that green circuit board. But there are a lot more segments than pins, which begs the question, how do they pull that off? What gives? And the answer is LCD multiplexing. So in short, where that screen from our demo had one common backplane, the F91W's LCD has 3. That means 3 common pins, and the rest, 24 of them, are segment pins. Whereas in the demo, the COM pin was linked to all of the segments, in this watch, each common only touches about a third of the segments. And whereas in our demo, each segment pin was linked to 1 segment, in this display, each segment line is linked to 3. The important thing here is that each segment that you want to address individually will have a unique common segment mapping. Okay, so yeah, I admit, that diagram was a lot to take in. To make it easier on ourselves, let's consider one segment in isolation. This is segment A of the last digit in the clock, which ticks the seconds. We would call this COM2 seg19, just numbering each pin from the left to right. You'll see that while COM2 is linked to a whole lot of segments, 24 of them all tinted in red, seg19 is only linked to the 3 segments tinted in blue. Only the purple segment, segment A of the seconds display, is linked to both COM2 and seg19. And that's the key to how we can address it individually. So before we do this ourselves, let's see how the F91W energizes this segment. Since the watch ticks once a second from 0 to 9, this top segment will be energized and de-energized fairly often. It's off when displaying the digits 1 and 4, and it's on the rest of the time. We're going to use a 1990s era Tektronix 2211 scope to visualize how the F91W achieves this. So here I have my F91W movement plugged into these oscilloscope probes, and the scope is showing us COM2 up top and seg19 on the bottom. So COM2, seg19. Technically, that's the inverse of seg19, but bear with me for a moment. So the interesting part comes when we subtract seg19 from COM2. So now we're seeing a lot of different waves, but the key is that there's really two peak voltages, plus or minus 3 volts and plus or minus 1.5 volts. Okay, so what did we see here and what can we learn from it? First, right at the outset, we saw the two waveforms separately. We saw that the COM waveform didn't change at all. It's just delivering 3 voltage levels repeatedly. We also saw the seg waveform with just 2 voltage levels and that it changes from time to time. Next, when we subtracted one from the other, we saw several different waveforms, but really 2 peak voltages, plus or minus 3 volts and plus or minus 1.5 volts. This tells us the voltage we need to energize a segment. This is a 3-volt display. So you might be asking yourself, in that middle photo, the segment only hits 3 volts about 1/3 of the time. Why is that? What about those other moments in between the plus or minus 3-volt peaks? And the answer is, those are time slots for the other segments. Remember, seg19 is controlling 3 segments on this watch, and we're only looking at it in relation to COM2. COM0 and COM1 are also doing their thing, and plotting seg19 against each of those would yield a different trace. So our workshop, the prepared, also has a more modern scope with 4 inputs, and we can use that to visualize the waves in more detail. Here we have our segment 19 waveform in yellow, and our COM0, COM1, and COM2 waveforms in cyan, pink, and blue. It's actually easier to see this if I stack up all the COM signals. So looking at the top there, you can see 6 distinct phases in the period of this wave. COM0 has a beat at 3 volts, then 2 beats at 1.5 volts, a beat at 0 volts, 2 more beats at 1.5, and then 2 more beats at 1.5 volts. Basically, over the course of the wave, each COM signal has a chance to be at its maximum and minimum value once. And the other signals hang out at 1.5 volts in between to give them their turn. This is how we're going to get to the key terms for this slide, duty and bias. With 3 COM lines, we have 3 chances for each common to hit its maximum and minimum voltages. That makes this a 1/3 duty waveform. Not coincidentally, that corresponds to the number of COM pins that we have. Bias refers to the intermediate voltage level involved in driving the LCD. Looking at the common waveforms up top, you can see 3 voltage levels, 0 volts, 1.5 volts, and 3 volts. That 1.5 volts makes this a 1/2 bias waveform, 3 volts divided 2 ways. If you had intermediate steps of 1 volt and 2 volts, it would be a 1/3 bias waveform, as in 3 volts divided 3 ways. These two terms combine to describe the waveform. 1/3 duty refers to the number of COM pins, and 1/2 bias refers to the single 1.5 volt bias voltage in between 0 and the LCD voltage. The line in purple, again, is showing us the difference between an on state and an off state for this segment, looking at COM0 this time. The important thing to note is the COM waveforms never change. Look at the state of the yellow seg wave right after that first cursor. In that trace at the top, it's high when COM0 is high, which adds it to 0 volts, segment off. When COM0 goes to 1.5 volts, no matter what seg19 is doing, the difference between the two can't be more than 1.5 volts. That's something, but it's not nearly enough to hit that 3-volt threshold, so the segment again remains off. Now look at it in the trace at the bottom. The segment line here is low when COM0 is high, which adds up to -3 volts, segment on. This same process is repeating 2 beats later with the opposite polarity. It's also happening the whole time with the segments attached to COM1 and COM2 during COM0's 1.5 volt phase. So each of those segments connected to seg19 are getting their own unique waveforms that can turn these segments on and off independently. So I added this slide late, but I realized you might be looking at this and thinking, how am I supposed to generate all these waveforms and bias voltages anyway? This seems complicated. Well, the good news is, if you pick a microcontroller with an integrated LCD driver, all this hard work is done for you. This is the datasheet for my current favorite microcontroller, the SAM L22 from Microchip. It's a lot like the SAM D21, but it has an LCD driver that's fluent in the language of segment LCD glass. So if you use a chip like this, instead of trying to figure out how to generate a waveform that turns off all of your segments, you can just write directly to display memory. Or if you want to go one level further, you can use vendor driver code that abstracts even that away and lets you deal with the LCD using function calls like a civilized human. It's pretty cool to drive both your logic and your display with one chip. And while this list isn't exhaustive, there's definitely a fair number of microcontrollers out there that you can use to drive an LCD without getting your hands dirty. Okay, so here's a question. How exact do you need to be with this? Like the waveforms we were looking at, do we have to replicate that waveform exactly to drive this LCD glass? And the answer is not necessarily. This LCD glass is a pretty simple thing. The SAM L22 likes to drive a 1/3 duty displays with a 1/3 bias waveform, which again involves intermediate voltages of 1 and 2 instead of 1.5. This display glass was perfectly happy with that. Again, the key points are to drive the segment above its threshold to energize it, to keep it below its threshold to turn it off, and to avoid any DC bias in the waveform. The SAM L22, with its integrated segment LCD driver, is easily able to check all of these boxes. Okay, we'll recap later. For now, we're rolling right along into section 3. We've covered the basics of LCD technology, and we've talked about how complex displays use different multiplexing schemes to drive displays with more segments than pins. Let's take those lessons and apply them to another Casio watch, the Casio Databank. This is a really cool watch with a lot of segments and a lot of buttons. It would be a blank canvas for displaying all kinds of cool information if we could figure out how to drive it. So let's figure out how to drive it. But first, let's take it apart. What do we see inside? Well, we have a backplate and a rubber gasket, and then a circuit board sandwiched in between two assemblies, one for the battery and one for the display. The circuit board itself has 55 exposed LCD pads, 28 in the top row and 27 in the bottom. Finally, we glossed over this point earlier, but I do want to point out the 2 elastomer strips sitting in the LCD assembly. These are commonly called zebra strip connectors, and they're the way the LCD actually connects to the circuit board. I do want to stop here for a quick detour on these elastomer strips, because if you do try to upcycle an LCD, you're almost certainly going to run into them. These are called zebra strips because they have many conductive stripes. You might also see them referred to as ledge connectors, since they mash up against the ledge of glass with the electrodes, which you can see reflected there in the glass. The idea here is that your display's electrodes have the exact same spacing as the pads on your PCB. And the zebra strip is way denser, so when it gets squished in between, there will be at least a few stripes making contact, which makes a vertical connection between the board and the glass. They do require very precise alignment, especially for a fine-pitched LCD like the one on a wristwatch. But on the plus side, any gadget that uses this technology is going to come with a strip that works and hopefully an enclosure that holds it in place precisely. Just don't lose it. Okay, back on track. Let's reverse engineer this databank LCD. To do it, we're going to need some tools: scissors, an oscilloscope, and blue painter's tape. Actually, later on, I reshot some of this with Kapton tape, but you can just use plain Scotch tape. All we're doing is taping over one pad to break the connection between the LCD glass and the PCB. Why are we doing this? Well, we're doing this because some of these pins are common pins and some of them are segment pins. And before we do anything else, we're going to have to figure out which ones are which. So with this one leftmost pin covered up, we reassemble the watch and we get this screen, which looks pretty similar. Not much has changed. But there's this neat trick with a lot of Casio watches. If you press both left buttons and the bottom right button at the same time, oops. There we go. You can turn on all the segments in the watch. When we do that, we can see that we lost 5 segments, 2 of them in the dot matrix and 3 down there in that year display, which brings us to the first guideline for reverse engineering these things. If a few segments turned off when you covered a pad, you've found a segment line. This should make sense if you recall our diagram from earlier. The COM line sweeps across a vast swath of the display, but the seg line only touches as many segments as there are COM lines. The fact that we lost 5 segments when we covered this pin strongly hints to me that there are 5 COM lines. It's not a guarantee, sometimes segments can be shared, but that is my suspicion at this point. Okay, moving on. Let's try covering up one pin on the opposite side of the board. What happens then? Answer, we lose a ton of segments, which brings us to the second guideline. If a lot of segments turned off when you covered a pad, you found a common line. This should follow from the diagram, but let's just throw it on screen again. The COM line intersects with as many segments as there are seg pins. So if we had 5 COM lines, we'd expect losing one to lose us about 1/5 of the segments. Okay, so now I'm just going to start covering up pads on the right side of the board. Here it is with 1 pin covered, and covering a second one. Again, we lose a big chunk of the display. This is another COM line. Third pin, another 20% of the display is gone. Fourth pin, only 50 segments remain, 34 in the dot matrix and 16 down at the bottom. And with 5 pins covered, the whole display goes blank. So get this, by covering 5 pads with plain old Scotch tape, we've discovered not just which pins are the commons, but also half of the segment mapping. Because if you look at the segments that were left when only that last COM was working, COM 0, again, numbering from left to right, we know all of those red segments must be attached to COM 0. Working backwards based on when we saw the segments turn off, we have all of the COM lines mapped out. Moreover, we can combine that with what we saw when we taped off the top left pin, seg 0, again, numbering from left to right, and we now have full segment addresses for 5 segments of the display, those 2 in the matrix and the 3 on that bottom row. So there's one last step to know how to drive this display, and that's to figure out the voltage required to turn on a segment. We'll use the scope for that, but before we do, I find it helps to locate one segment that toggles fairly often. Ideally, I'd like to find a segment in the ones place of the seconds display, since all of them change at least once every 10 seconds. In this case, I just had a lucky guess. I just taped off one of the pads on the right, and it was the one that controlled the seconds display. So with that, to the scope. I really wanted to do this piece live, but it's a bit fiddly to keep the movement clip down while measuring, so I have it on video. But if you look at the scope traces, the key is that you can see the peak-to-peak voltage of the COM and the seg pins, and you can also see the purple waveform changing, de-energizing the segment from time to time, so we know we're on the right track. Okay, so what did we learn from this? Well, we know the duty is 1/5 because there are 5 COM pins. We also see 3 non-zero voltages, making this a 1/3 bias waveform. The most important thing, though, is we were able to measure the peak-to-peak voltage on the COM and the seg pins, and it looks like just about 4.1 volts. I actually measured this again later with a full battery and got 4.5 volts, but either way, it means my favorite LCD-oriented microcontroller, the SAM-L22, can't drive this display since it maxes out at 3.6 volts. But that doesn't mean it's impossible. I'm going to throw up that list from earlier, the one that showed chips with built-in LCD drivers, and I get the sense that this PIC16 has the oomph required to drive a 4.5 volt LCD. With 53 pins, it might not be able to drive all of the segments, but you could get pretty dang close. Okay, so let's recap this back third of the talk. We talked about multiplexed LCDs and addressing them by their common and segment pins. We looked at some of the waveforms that drive these multiplexed LCDs, and we talked about how duty and bias work. We talked about microcontrollers with LCD drivers that can help wave away some of these complexities. But we also saw how understanding these concepts gives us the ability to poke at LCDs in the wild and understand how they work. So it looks like we have time, so this is the bonus round, in which your speaker discovers that it's actually not that impossible to have your own segment LCD manufactured. This is the Sensor Watch dev board. It's in a feather form factor, and if that LCD layout looks familiar, there's a reason. It's specifically designed to match the pinout and layout of the F91W LCD. Why do a custom LCD? Well, the answer will vary from project to project, but in my case, I needed something specific. I wanted to make a board whose display matched the one on the Sensor Watch, so folks could test their apps more easily. To do that, I needed a screen that matched the F91Ws. You may also have design constraints. In my case, the existing F91W LCD was too small, too thin, and too fragile for this application. I tried it. It barely worked. I almost crushed it to death. This also only makes sense if you want to make a lot of them. So there's an initial tooling cost that can range from hundreds to over $1,000. I bit the bullet and did it because I hope to end up making a lot of these, but it's not ideal for making just 5 or 10 of something. But if you want to make 1,000 of them, you could end up spending as little as $1 each for a display this size. And if you wanted to make 10,000 of them, you could end up spending even less per display. One note, this is not to say that you can spend $1,000 for 5 prototype displays. You'll need to work with a manufacturer, and their whole process is oriented around figuring out the tooling and then making a reasonably large run of the same display. So it's not for everyone. But if you're building a product and you need something more custom, this process could make sense for you. Okay, so to make a custom segment LCD, You can use just about any vector graphics program, Inkscape, Illustrator, whatever. Your manufacturer may ask for an AutoCAD DWG of your design, but I was able to provide an SVG and it worked just fine. Personally, I used Affinity Designer to lay this out and it worked great. Remember, you can't draw more segments in your design than you can actually control. The number of segments you can drive is going to be equal to the number of COM pins in your design times the number of segment pins. But you can tie multiple segments together. For example, the PM and the signal icons, those are just one addressable segment. Same with those 3 segments of that weird number in the date display. You can turn all 3 of those segments on or off, but you can't control them individually. It's a trade-off, right? It makes that position only good for displaying the numbers 1, 2, and 3, but it means you only need 4 addresses for that digit instead of 7. Next, you'll want to draw up a datasheet. Some LCD fabricators will just take your drawing and make it happen, but if you provide some more details, you can have a lot more control over the outcome. So you'll want to specify dimensions. Remember, there are going to be manufacturing tolerances, so this is just a nominal dimensions sort of thing. They will come back to you with final dimensions for your approval. You'll also need a bit of margin on the edges because they need to seal the glass and you can't have any segments in the area where they do that. Optionally, you can specify a segment map. They can just pick a map and route it for you, but if you have constraints like I did, you can specify it. Note that they may not be able to accommodate your segment map. Routing an LCD is a lot like routing a single layer board. So if your layout is particularly complex, they may not be able to route it. But you can at least specify certain things that are important to you, and you can hope that they can accommodate it. Finally, you need to specify some required parameters, and I'll just go over them very quickly. TN, or twisted nematic, is the most common type of LCD. It's cheap and it works well for segment LCDs. Viewing direction. Basically, it refers to the angle folks will view it at. It's like the clock hands. If they're looking at it from slightly below, like a wristwatch, it'll be 6 o'clock. If they're looking at it from slightly above, like a desk clock, it'll be 12 o'clock. Polarizer mode. There's 2 pieces to this. Positive means it's a light display with segments that darken when they're energized, and negative is that cool inverse look where it's all black and the segments turn light. Transflective has to do with the polarizer on the back of the glass. Transparent is totally see-through, like a heads-up display. Reflective is totally opaque. Transflective tends to be the best of both worlds. It has a backing layer so you can see the display, but it's semi-transparent so you can also light it from behind. Driver method we talked about. Duty will match the number of COM pins in your design, and your LCD driver's datasheet will likely recommend a bias scheme for a given duty ratio. Operating voltage, again, you just want to ask for something that works with your chip. They made me a 3-volt LCD. It is pretty standard. Temperature, I didn't really care about. And then connection method. I asked for zebra strip, which meant I needed to make that 3D printed enclosure to hold the whole thing together. It also meant that I had to find some zebra strips on eBay. You may want to have them crimp pins on, but this part is entirely up to you. Finally, there are some notes, but the only one I want to call out is the filling port. So after they etch your glass, they need to fill the inside with fluid. That's the liquid in a liquid crystal display. This means there will be a filling port bumping out from one side of your display glass. It's just a small bump of glass, about an extra millimeter. I asked for it on the bottom, they put it on the left. In my case, it really didn't matter. Just know that you'll have to account for that bump in your enclosure design. And again, they will send you a final data sheet with all of these dimensions for approval. Finally, you don't have to do this, but I just did it because I wanted to be sure it would work. At some point, someone is going to have to route your LCD. This means physically laying out the traces that will connect all of the common and segment lines. Again, it's a lot like laying out a single layer PCB. All the lines have to connect, they can't cross each other, and there are no vias to help you. I really don't know what tools the LCD fab houses use for this. All I know is I used Eagle and did some auto router hacks to get a sense for it. I laid out a schematic with some parts that resembled the pad layout for my electrodes, some single pin parts for icons, and some 8-pin parts for the segmented digits. And I connected them up to the COM lines I needed to lay out. I basically arranged them roughly the way I wanted them to look on the LCD, and I had the auto router take a stab at it. Same thing for the segment lines. I just assigned them all and let the auto router do that job for me. Okay, so here's a question. Are these best practices? Is this the right way to do this? And the answer is, I don't know, really. If anyone in the audience has any insights as to what tools they use to route these kinds of things in the real world, I'd love to hear it. Please reach out. For now, just know that it's what I did, and it worked for me and got me to a working display. Okay, so wrapping up. I hope this talk offered some insight into making use of LCD technology. We talked about how these little pieces of glass are great for low power projects. We talked about how they work and how to recognize the different kinds of waveforms that drive them. We also talked about how you can drive them with peripherals designed for this exact purpose. We talked about how these displays are out there in gadgets all around you. And we talked about how you can unlock their secrets. Finally, we also went over the basics of how to design your own LCD for a device if you can't find anything in the salvage bin that fits your exact needs. So that wraps it up for me. These slides are available on the Remoticon slide share, so you can download them and check out some of my notes. And I'll be on Discord if you have any questions, but you can also ask any questions on Twitter @Jose Castillo. Thank you.